Thank you. It's a great pleasure to be here. Yes, I'm going to be talking about a measure of information for reasoning about data selection and how data influences the behavior of our models. In general, there are a number of phenomena that are becoming increasingly hard to describe with existing theoretical frameworks. For example, information theory tells us that we don't get new information from deterministic transformations, yet synthetic data is everywhere. We know pseudo-random number generators are ubiquitous and very useful, and there are systems like AlphaZero that learn sophisticated strategies just from self-play. The Shannon symmetry of information and Kolmogorov complexity and algorithmic information theory also suggest that information content in data is independent of ordering, but we know that there's an arrow of time and all sorts of data sources, which is crucial for our models to be able to learn useful representations. An LLM will learn a lot more from English ordered left to right than in some arbitrary ordering. And also that likelihood modeling, how we typically train our models, is merely distribution matching, suggesting that our models couldn't possibly go beyond the generative processes that created the data that we're using for training. But of course, we see emergent phenomena where models often do go beyond the data that they've been trained on. So to help resolve these paradoxes and reason about the value of data, particularly for out of distribution generalization, we introduce a new measure of information called epiplexity. It stands for epistemic complexity. The paper is very searchable. If you just type in epiplexity, it will be the first results. And this also helps us think about how to evaluate models when we don't know how they're going to be applied. So Edward actually mentioned this is a deficiency of many existing evaluation frameworks. This is something that epiplexity is helping us reason about. And what's really missing in existing mathematical constructs is the idea that our models are computationally limited. We don't have unbounded computation, and we want to target useful information content rather than information content in general. And so, important to being able to do this is separating out random information, unpredictable information that is not going to be useful for training our model from structural information content that actually could lead to an interesting representation that we could then apply in a bunch of different downstream settings. So in this slide, I'm showing three different sources of information. The first row shows um, data that has both low random and low structural information content. The middle row shows natural images and a block of code, which does have useful structural information content for training our models, also some amount of random information. And the bottom row just shows white noise. So that's going to be incompressible. It's going to have high Kolmogorov complexity, but it's going to be completely useless for training our model, which contrasts with other sources of data, which also might be relatively incompressible, but actually contain a lot of useful information content for training our data. So, to reason about these questions, we introduce epiplexity. Epiplexity defines the structural information a computationally bounded observer can extract from data, and it correlates very strongly to out of distribution generalization performance. So, if a model is able to discover, for example, all sorts of interesting circuits in data, then often that can be recycled towards good downstream performance in various different settings. Formally speaking, epiplexity is the size of the model that has the optimal minimum description length representation of data under computational constraints. The remaining parts we call the time bounded entropy. So that's kind of like the unpredictable sort of aspect of the data. We can measure or approximate epiplexity quite simply looking at the area under the loss curve above the final value of the loss. So this is an easy thing for us to go and operationalize immediately. We also have finer grained estimates for epiplexity in the paper where we propose new ways of doing compression. We've considered using epiplexity to measure out of distribution generalization in a variety of settings, and also to shed light on why certain modalities of data seem to lead to representations that transfer much more readily to other settings than other modalities of data. So it's been observed, for instance, language seems to lead to representations that are relatively more universal than images. So you can train LLMs just on next word prediction, and they can be used quite successfully, for example, in time series forecasting, which is something that we showed. You can also use them for things like generating stable inorganic crystals with energetically favorable properties, which is certainly not something that you would expect. But it turns out that language data often has much higher epiplexity, much more like structural information content that you might expect to be able to recycle in these other modalities. We've also used epiplexity for things like online data selection and to understand curricula for curriculum learning that will lead to more general representations. There are many, I think, fascinating directions for follow-up work, especially in understanding, how data is really going to influence our model behavior and the intersection of structural information content across different modalities of data. All right, thank you.